We'll talk a little bit about work, energy and power over a couple of videos in this particular week in this module. I've divided those out a little bit, so energy is in one and work and power are in another. So let's talk a little bit about energy. It's one of the biggest needs of our society, one of the next questions over the next few generations. What kind of energy we'll be using and how we'll be using it and what it will be doing for us. But some basic concepts are quite helpful, and this is part of that developing students as citizens, not just scientists, that they actually understand something about the ways in which society works with energy. Energy on Earth comes basically mostly from the sun. If you think about the fact that all of our food comes from green plants, which use solar energy and photosynthesis to create energy, and that is that helps to feed us and all other living things and the things that we eat and so on. All the weather, which in turn drives things like hydroelectricity, sorry. Windmills, wind turbines are driven by the weather, which is effectively powered by the sun. Fossil fuels are basically ancient plants, so that's driven by the sun as well. It's stored up sunlight, fossilized sunlight, if you like. Or the other thing is nuclear fusion reactions in the sun, which is, and nuclear fission reactions on Earth. So a fission power station is a source of heat. Geothermal, some of that heat that comes out from lava or from geothermal vents and so on is still left over from the creation of this planet about 4.5 billion years ago, because we've got this insulating layer of rock, so it's still hot from when it was made all that time ago. But a lot of it also is from nuclear reactions inside all that rock. So a lot of that geothermal heat is nuclear energy as well. It's fission. So as I say, either fusion in the sun, and we talk about nuclear fusion as a potential future source of energy, and they always say it's about 40 years ago. I remember them 40 years ago saying it's about 40 years away that we'll have harnessed nuclear fusion as a clean, safe source of energy. But we do have this massive nuclear fusion reactor that's overhead every day of the year that we can actually harness. So using solar and wind and the various other things that are driven by that nuclear reactor is probably not a bad plan. The laws of thermodynamics, you may actually like to, at some point, Flanders and Swan Law of Thermodynamics. On YouTube, search Flanders and Swan Law of Thermodynamics. There's a great little song about the second law of thermodynamics in particular, but the first and second laws. It's good fun. But energy in general tends to go from more useful to less useful forms and end up as heat. So the incoming solar radiation is not mostly heat. I mean, we feel hot when we're in the sun, but it's not mostly heat. It's mostly short wavelength, ultraviolet and visible light, which is a quite useful form. It runs photosynthesis and a whole variety of other things. And then that gets changed into chemical energy in foods, and that gets changed in the end into heat as the living thing that's eaten the food runs around and does its business. So the energy pretty much all ends up as heat, and the heat is radiated off into space. The Earth's total energy balance, how much we're getting in, which is basically entirely from the sun, versus how much we're sending out, we're radiating out into space, should be close to zero. Because if you imagine a bank account that has money in and money out, if the two are equal, it stays at a constant balance. If one or the other is predominating, you either go into big debt or you end up getting rich. The Earth's energy balance is similar, that if we retained more energy than we radiated off into space, we would overheat. If we radiated off more than we got, we would freeze. So we want the balance to be close to zero. Greenhouse gases do mess with that balance slightly. I might talk about this a bit more when we talk about radiation and scattering, although it's closer to chemistry than physics in some ways. But the greenhouse gases basically capture that heat, that infrared radiation that's being radiated off into space, and capture it in the atmosphere and warm the atmosphere instead. So that's basically what's going on with climate change, is that we're getting more energy into the system, and that doesn't just make it hotter, it also powers the wind the cyclones, the hurricanes, the floods, the droughts, the whole weather system just gets more extreme, is the result of that. So that's basically about energy. The SI unit is the joule. You're probably familiar with this from junior secondary. James Joule was a British scientist, but more importantly a brewer, made the good stuff. And as for the Newton, lowercase joule for the name, but capital J for the symbol. And we also use the joule for work as well as energy, because energy and work are related strongly to each other, as we'll discuss in the next video. A list of some forms of energy, and you've kind of done this. I guess you have talked at least to your students about kinetic and potential energy. So various kinds of radiation carry energy. The shorter the wavelength, the more energy. So ultraviolet contains more energy than infrared. X-ray contains more energy again, and so on. Anything that has mass and is moving has kinetic energy. Anything that is in a gravitational field and has mass has gravitational potential energy, unless it's right at the very center of the Earth or whatever is causing that gravitational field. As soon as you move away from the center of gravity of another object with mass, you've got some gravitational potential energy. It takes work to lift you up, and you get work out if you come down again. So things like those grandfather clocks, I don't know if you've ever played with one where you pull a chain and lift a weight up to the top, and the gravitational potential energy is what drives the clock and gives it its energy, and the weights gradually go down. So to wind the clock, you lift them up again to the top. Or chemical potential energy as well. Spring potential energy, if a coiled spring is a way of containing and storing energy. We can have chemical potential energy in batteries, or in petrol. The fact that it can burn, it means it's got stored energy that we can use, and so on. So lots of different forms. As I said, we usually change from a more useful to a less useful form of energy, but do something useful with it. So I'm under some very bright lights in the studio. We're changing electrical energy into light energy. The electrical energy is effectively gone. The electrons still continue around the circuit, and we'll get onto that a little bit later, but that electrical energy has been transformed to light energy. That lights me for the video and then heats the atmosphere in this room, which is getting fairly warm, and it ends up as heat, as most things do. In a car, you've got that chemical potential energy in the fuel, turns it into kinetic energy, a lot of heat energy. Remember that car engines are only about 20% efficient, so a lot of the energy is just wasted with friction in the engine and the byproducts of an internal combustion engine and so on. So there's a lot of energy that goes that way. We turn it into kinetic energy, and then we put the brakes on and we turn that into heat as well. If you've ever seen the brake discs of Formula One cars, sometimes they're actually glowing red hot because they've been accelerating up to high speed and then braking to low speed in corners, and they're trying to dissipate all that heat as energy in the brakes through friction. So kinetic energy, as I said, ends up in the brake discs and pads, or the brake drums if we're going old school, which is released out into the air, and we do send off that heat energy into space. In living systems, as I said, visible and ultraviolet radiation turns into chemical energy through photosynthesis, and then say you have eaten your breakfast of plants and or animals, because remember we could also talk, this is more biology and junior science, but plants as producers that produce energy from the sun, and then first order consumers that are the herbivores that eat the plants, and then second order consumers that are the carnivores or omnivores that eat the animals, and so on. So the energy for the whole system comes from the sun, and about 90% of it is used up at each stage by that thing living. So if you're eating, probably fish are the best example, because you might have a little fish that eats plankton and a bigger fish eats the little fish. A big tuna or something eats the little fish, and a shark eats the tuna, and then you eat your flake in your fish and chips, which is the shark. At every one of those steps, about 90% of the energy has been just used up. And so it takes a lot of plankton and a lot of little fish to make a pound of shark, a kilo. Why am I saying pounds? So a lot of the energy at every stage is what we'd call wasted. It disappears out into the atmosphere as heat and is radiated off. And that's kind of the nature. There's no 100% efficient process. And that's part of what the laws of thermodynamics say as well, that there aren't processes that are perfectly efficient. A few little formulae and calculations. For kinetic energy, you're probably familiar with this one, kinetic energy. Some people write it as KE, but E subscript K is probably better because it just reminds us that it's all energy. EK is a half mv squared, half the mass times the velocity squared of the object. For gravitational potential energy, EP is mgh, the mass times the acceleration due to gravity times the height that it's lifted through. And for spring potential energy, if we're compressing a spring, half kx squared, you can see that that's actually kind of analogous to the half mv squared. It's a similar kind of structure of formula. So we might talk a bit about compressed springs as well, whether they're stretched or compressed and so on. So a number of ways of calculating forms of energy. So if we can calculate by going, all right, this golf ball is at the top of the 300-meter building. It has a mass of 0.032 kilograms. So therefore it's got potential energy. EP equals mgh. So its mass times 9.8 times the height, 300 meters. So we know how much energy it's got. If we drop it, and if we again ignore air resistance, then just before the ground, just before it touches the ground, all of that will be kinetic energy. So we can use the same number and say, all right, we still know the mass. We know the kinetic energy is a half mv squared. And we know what the energy is because we just converted potential into kinetic. So we can calculate what the velocity will be just before it hits the ground based on energy. We could also calculate that just using the acceleration due to gravity and the distance, but we can also work it out through the energy. So energy is converted from one form to another. Roller coasters, you go on that clanking, 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 drive up to the top, and my hand disappears. It's a magic trick. You go up to the top, and then it's basically all gravity. You start with a lot of potential energy, convert to kinetic energy at the bottom of the hill, you're going fast. Go up the hill, you slow down because the kinetic energy is converting to potential energy again, and so on. Because there's friction, because there's always waste, you'll notice if you look closely at a roller coaster that the first hill is the highest, and every hill from there on has to be lower because you've wasted some heat, lost some energy, and therefore you wouldn't get over a hill that's the same height as the original hill. Every hill gets lower until you get back to the start.